So, yeah, if you're watching at home, exam 3 is a week from today in class. So it's going to be a little bit of chapter 5. This is the chapter 5 stuff I'm going to do in class today. All right, so I mean, you guys have to know, you have to know some stereochemistry and relationships. Like, I expect that you'll know everything that we've done up to now. So you should also, but I'm not going to ask like explicit questions. Except for there's a little bit of 5 that we'll do in class today. That'll be on there. Chapter 7 is substitution and elimination. That's obviously going to be kind of the main bit. Chapter 9, which is alkynes. And then a little bit of chapter 10, which is the free radical halogenation I did in class one day as well. And there's not much of that. I'll get you some section numbers. The final exam then is cumulative, covers everything we've done. It's on Saturday, May 8th at 9 a.m. That's the first exam slot. Congratulations. I've gotten this question a lot. It's in the syllabus. I've put it in announcements. I've announced it several times in class, but just one more time. If you decide you would rather have your midterm averages count as your final score, that's fine. You have to do the final packet no matter what. If you've aced every midterm, you still have to turn that final packet in. But say you have a 94 average on exams 1 through 3. You can just tell me that you would rather your final be a 94 and it's a 94. If you arrive on May 8th to take the final, your score counts. So you can't take the final and think, crap, I bombed that, use my average. It's not a drop, it's not a highest of. You have to, you don't have to actually tell me, right? You don't have to tell me you're going to use that average, you just don't show up for the final. If I sit down and I don't have a final, then okay. I'll record everybody who's here for the final when we do that. So yeah, the final's 3 hours. I'll give you 3 hours. I'm not going to write necessarily a 3-hour exam. I would like for you to have plenty of time. I'm not saying you'll be able to just dawdle, but you should have plenty of time to finish it. And as I was saying, the university publishes a final exam schedule every semester that will tell you when your finals are. Your professors are obligated to give you an opportunity to take the final in that slot. They can offer other times if they want. They can not give a final. But if it's, like I know sometimes faculty, I've been tempted, I've never done it, but like if my final's the last day at noon, like I want to be done before that, so I say, oh no, we're going to do the final earlier. Like I can offer an alternate time, but if you tell me you want to take the final that last day, I have to let you. So most faculty are pretty good about these things, but every now and then either because they don't know or they're jerks. Some of my colleagues are jerks, a few of them. They might try to pressure you into taking the final when they want you to. There's also a rule, and I don't know how this gets handled, there's a rule that you're not allowed, like if you have 3 scheduled finals within 24 hours, we have to give you a break. I don't know how that works exactly, but anyway, questions you should ask. Yeah? Chapter 9 is alkynes. Everything in Chapter 9 is on this exam. Yep. All right, so the Chapter 5 bit I didn't do during, we had a snow day that cost us this bit in Chapter 5. Chapter 5 was stereochemistry. I know I throw around these numbers, and like you guys have the book memorized. Yeah, good. They can hear me at home. All right, so the thing I didn't get to cover is this thing called Enantiomeric Excess, or percent EE. So we have, traditionally, there is a sound scientific reason for why we describe mixtures of enantiomers the way I'm about to describe. Right? Like generally speaking, you describe mixtures as a percent. Right? If I have a bucket of fruit, say I got 20 pieces of fruit and 13 of them are apples, you would say 65% of your fruit is apples, right? There's one professor in a room of 25 people, so 4% of the room is professors. With enantiomers, we don't do that. All right, so enantiomers present a weird kind of problem. Usually when you're describing a mixture, it's really clear, the boundaries between the stuff is really clear, right? In this room, if somebody walked in, they would immediately know that you were students and I'm a professor, because even though I look the same age as you, like I'm standing at the front of the room talking. Wow, nobody, you're either really good or you're not listening. All right, you laughed, which is gonna cost you. All right, so, with enantiomers, remember, enantiomers have exactly the same energy. They have the same stability. In an achiral environment, they have the same physical properties. So if I have a mixture of enantiomers that is completely pure otherwise, right? So it's just the R, it's just the S. There's not really any way for me to directly measure how much is in each one. There is today, okay? With late 20th century technology, this is pretty easy. With 19th century technology, it was impossible except for one thing. All right, so I'll write this down. Write that down, if you're the type who writes stuff down, and then I'll explain it. All right, so chiral molecules will rotate the plane of polarization of polarized light. So it turns out that light, polarized light, is chiral. All right, so light is made up, you've probably heard the phrase electromagnetic radiation. Maybe you've had some physics and studied this. Light consists of an electric vector and a magnetic vector. All right? When you put these two things together, if the light is polarized, those vectors end up making the polarized light chiral. So kind of an important thing here, put this over here. Think how to put this. I said this in passing, and maybe you didn't get it. I mean, not that you didn't understand it, you just missed that I said it. So, two enantiomers will behave identically in an achiral environment. And you can think about that, right? Like my hands are chiral. They're the mirror image of each other, and they're non-superimposable. All right, so this surface, this table is flat, so it's achiral, right? I take my two chiral objects, my two enantiomers, they each lay smoothly on the flat surface, okay? Achiral table, enantiomers, identical interactions. If I'd been thinking, I would have brought my gloves. If it was February when I normally do this lecture, I probably would have had gloves, right? The gloves are chiral. If I try to put my right hand and my left hand fit differently in a right-handed glove, right? If you've tried to put a left hand into a right-handed glove, you know it doesn't work very well. Try to put a right foot in a left shoe, doesn't work. So just as two enantiomers will behave the same in an achiral environment, they will behave differently in a chiral environment. All right, so if I take my two enantiomers and I put them in a chiral environment, those two enantiomers are going to behave differently all of a sudden. And the reason for that is, essentially, you've got a diastereomeric relationship at that point. right? If I've got R and S, right? If I take an R molecule and I expose it to an achiral reagent, say it makes a complex of some sort, and then I do that with an S, and that makes a complex with the achiral reagent, then these are still enantiomers, right? So on the left, these are enantiomers. Over here, these are enantiomers. All right, if I do the same thing if I expose my two enantiomers to something that's chiral, and let's say that chiral thing is R. Doesn't have to be, but let's say it is. Then what I wind up with is an RR pair and an SR pair. Those now are diastereomers, right? Diastereomers Diastereomers behave differently in all environments. Right? Think about cis-trans. Right? If I've got the two big groups equatorial, that's different than having one big group equatorial and one group axial. All right? Cis-trans isomers will have different stabilities, different energies, different properties. So an enantiomeric relationship, if the environment's not chiral, that relationship's the same. Diastereomeric relationships, under all circumstances, are different. It may not be very different. It may be hard to separate them, but they're different. Okay, so now, if we expose two enantiomers to plane polarized light, that plane polarized light's chiral, and it's the same chirality for both enantiomers. Right? My R enantiomer interacts with the plane polarized light in a diastereomeric fashion to the S enantiomer interacting with the plane polarized light. So the effect is different. And in the late 19th century, early 20th century, when folks were trying to figure this out for the first time, plane polarized light was basically the only chiral object they had with which to probe enantiomers. Okay? So, the magnitude of the rotation is the same for both enantiomers. All right. If I've got one molecule that rotates, if I've got one enantiomer and it rotates plane polarized light 15 degrees, its enantiomer will rotate plane polarized light 15 degrees. The difference is they go different directions. Right? So if one enantiomer rotates the plane of polarization clockwise 15 degrees, the enantiomer is going to rotate that plane of polarization counterclockwise 15 degrees. There's really, at this point, not a way to predict, based on the structure of a molecule, which direction that plane of polarization will be, much less its magnitude. So I can't just draw a molecule and say, what's the rotation with this molecule? But if I give you a molecule and I tell you its specific rotation, I say this molecule rotates the plane of polarization minus 82 degrees, you know the rotation for its enantiomer. Okay? So again, right, if I've got the plane of polarization, I should get on camera for this. Right, if the plane of polarization is straight up and down, and I pass it through a chiral substance that is not racemic, right? There's more of one enantiomer than the other, that plane of polarization is going to deviate one direction or the other. Fair enough?
So something just stated to it said there's no optical activity?
Right. So that then brings us to, I'm going to have to cover some stuff up at this point. So let's think about some different situations. And I'll write some symbols here. So if you have a pure enantiomer, that is, there are no other products in it, there are no other chemicals in it, there's not even the other enantiomer. Every molecule in your sample is one enantiomer of one molecule. Then we would say that the observed rotation, so rotation in this is alpha for some reason, so the observed rotation is going to equal the specific rotation. There's a couple of things with this that you do not have to know for this exam, but they're cool things to know. The 25 here is the temperature. Okay, so the magnitude of the rotation of the plane polarized light is temperature dependent. If you measure this at 40 degrees, it won't equal what it is at 25 degrees. That's kind of, I mean, maybe not obvious, but it doesn't surprise you. A lot of things change with temperature. The other thing that's kind of interesting and is not really, doesn't jump out at you here, this capital D, I think I have this right. Like I said, you're not going to have to regurgitate this back to me on an exam. The magnitude of the rotation of plane polarized light is wavelength dependent. All right, so plane polarized 300 nanometer light will rotate differently than plane polarized 400 nanometer light. The specific rotation we use in these experiments corresponds to a line from the sodium spectrum at 546 nanometers. It's called the D line of the sodium spectrum, and so the specific rotation will have a little d there. Right? Again, this is not something you're going to have to use here, but some of you, this does come back around in biochemistry. So most biomolecules are chiral. I think I mentioned this when we did chapter 5. Right? So a lot of biochemists will study these biological molecules, which are quite complicated, very large. And one of the techniques they use is called circular dichroism. In a CD experiment, you take a spectrum from like 200 to 800 nanometers of your sample, right? And so the plane of rotation, or the magnitude of rotation is going to vary along from 200 to 800. And so you get these crazy curves. Sometimes it's minus, sometimes it's plus. But you get enough data points that winds up being characteristic of the sample. And you can pick out like an alpha helix. Alpha helices look a certain way in a CD spectrum. Beta sheets look a certain way. You can sort of work out, you can get a lot of kind of qualitative data based on this physical phenomenon that a chiral molecule will rotate the plane of polarization of plane polarized light. So if you're working with small molecules, you don't need that much data. Right? We can just physically characterize it with one wavelength. It's a much simpler experiment. It's a less expensive, technically demanding experiment. So you could run it in 1895. Okay. So that's sort of, I'm doing possibilities here. So that's a pure enantiomer. The specific rotation is a physical characteristic of a molecule, all right? It's like a boiling point or a melting point or an IR spectrum. And again, you can't predict based on the structure what the specific rotation will be. Here in a minute, I'm going to show you the specific rotation for 2-butanol. If I said then, show me what do you think the specific rotation for 2-pentanol is, you'd say, oh, it ought to be about the same. Those are two really similar molecules. Doesn't have to be. So we are a little bit better at predicting this kind of thing now than when I was your age, but we're still not there. And if you could come out with an ironclad method to predict based on chemical structure what the specific rotation is, what magnitude, what direction it is, you'd probably win a Nobel Prize. You probably wouldn't make any money, but you'd win a Nobel Prize. Well, there's some money with that. Okay, so the other possibility, we got a pure enantiomer. Another is, what if we have a 50-50 mix of enantiomers? And I've already told you guys that this is called a racemic mixture. Or a racemate. In that case, if you have a truly 50-50 mix of enantiomers, right, so the plane polarized light comes in, it hits the positive enantiomer, that bumps the plane of polarization clockwise. Then it hits the enantiomer, that bumps it back to 0. Then it hits the enantiomer, bumps it counterclockwise. Then it hits the original, comes back to clockwise, or comes back to 0. At the end of that path, the sum is going to be 0. It's just going to back and forth around 0. They cancel out, in other words. All right, so that's why this got a special name. Remember, from the time that Van Hoff figured out that sp3 carbon could be chiral, and Pasteur separated enantiomers using crystals, from that time until, I don't know, the 1970s, really the only way we could analyze enantiomers was with plane polarized light. So everything around discussing mixtures of enantiomers incorporates this terminology. Like I said, it's a little unfortunate because it's a crappy way to describe a mixture, but we need to work with it. All right, so those are the two pretty obvious ones, pure enantiomer and a 50-50 mix of enantiomers. So what happens if we have a non-racemic mixture, okay? It's a mixture. We have some of both enantiomers, but we don't have a pure enantiomer, but it's also not 50-50. In this case, we have the enantiomeric excess. All right? The enantiomeric excess is the amount in excess one enantiomer is over the other. So it's like the percent of the major enantiomer in the mixture minus the percent of the minor enantiomer in the mixture. And if you think about this, let's say it's 80, or let's say it's 90-10. Right? So there's 10% of the minor enantiomer. It could be, let's say the minor in this case rotates light clockwise. All right, so that 10% rotates light 10% of the specific rotation distance clockwise. It takes 10% of the major enantiomer to bounce it back to 0. And then you've got 80% of the major left to knock it counterclockwise. Okay, so the observed rotation is not 90% of the specific rotation, it's 80%. So the percent EE is the observed rotation divided by the specific rotation. So again, you measure the specific rotation for a pure enantiomer, then when you get a mixture, you measure the observed rotation, and that will tell you the percent EE. All right, so basically, there are 3 things here. Experimentally, you got to know 2 of them to figure out the third. When you run experiments like this, though, there's something you also have to do that we maintain, and that is this only works if all you have are the 2 enantiomers. Right? If you've got a complex mixture, there's like 9 different chemicals in it, some of which are chiral, some of which aren't. There's no way to do this analysis. This analysis only works when I have a pure sample that is only a mixture of the 2 enantiomers. And then you can plug in this equation, right? So up above, we have 3 unknowns, 1 equation. Here, we can add this equation. The percent of the major is going to equal 100 minus the percent of the minor. Okay, so if I've got, if 90% of my mixture is the major, 10% has to be the minor. It's not 8% then plus some other stuff. Okay. So let's go through an actual problem. I'll come over here. Like I said, I told you I would. There is 2-butanol, and just for kicks, tell me if that's R or S. Got to vote for R. Anybody disagree? So just a reminder on how we do that. We got to assign priorities by atomic weight, right? O is 1, H, which is going back, is 4. Carbon and carbon tie. Next atom, carbon versus hydrogen. So this is 1, 2, 3. 1, 2, 3. That's clockwise to you guys. It's counterclockwise to me. All right, so this is clockwise. The 4 group is back. So this is R. All right. So draw the S enantiomer. Nope. The semester is old. Okay, so 2 ways of doing this. You can actually physically draw the mirror image. It's fine if you do that. You can keep the heavy atom skeleton the same in 2 dimensions and just change wedge to a dash. That's what I've done there. So this is S. All right, so what's the specific rotation for the R enantiomer? Okay, good. I've got a few shrugs of hand. You can't know, right? That's not a fair question. I mean, it's, if I were to ask that question on an exam, what's the specific rotation of this molecule? Somewhere there's got to be a hint. I've got to have given you some data over here. Maybe I gave you the information about the enantiomer. If I haven't, totally fair to just tell me you don't know. Let me look this up myself. All right, Specific rotation for the R enantiomer is minus 13.5 degrees. That means it rotates plane polarized light 13.5 degrees counterclockwise. I haven't mentioned it. This is an experimental thing. This goes like Beer's law, right? That minus 13.5, the specific rotation includes a standard path length, a standard concentration. Again, the same wavelength, right? If the path length is longer, the rotation's greater. Path length is shorter, the rotation's less. If the concentration's higher, there's more molecules to rotate the light, the rotation's greater. Lower concentration, less rotation. I'm not going to ask any of those questions. I think Wiley Plus has some of that. I tried to get them out of there if you go back in for this. Like they're crazy, like they'll make you, this is not a lab course, and we don't do this experiment in the lab, and I'll tell you why here in a minute. So, what is the specific rotation of S? Plus what? Yeah. So S is plus 13.5. Right? So now I have, by giving you the specific rotation of R, I've told you the specific rotation of S. Same number, different sign. The name of the R enantiomer, by the way, you might see like this. R minus 2-butanol. This is probably the thing I need to, like a lot of you are pre-med, pre-health, pre-biological something. The plus minus bit for enantiomers has hung around a little more in biology and medicine than it has in chemistry. And so you'll often see a molecule whose name includes a plus sign or a minus sign. All right? What that's telling you is what direction that molecule rotates plane polarized light. That, in the name, that doesn't give you a specific rotation, but it tells you this enantiomer is the plus. We do that because a lot of drugs, well, today, right, you can't get anything approved by the FDA or really any health organization without knowing everything about a structure. All right? Absolute configurations, all that stuff. But at times we have, and a lot of times when a natural product is first isolated, we don't know the absolute configuration. All we know is what direction it rotates plane polarized light. All right? So we will say this is the plus enantiomer, that's the minus enantiomer, and then we'll start working on like figuring out how many chiral centers there are, which chiral centers are R, which are S, but that usually comes a lot later. All right, so just R minus 2-butanol, so S would be S plus 2-butanol. Okay. So if this is a racemic mixture, the observed rotation would be 0. If it was pure R, the observed rotation would be minus 13.5. If it was pure S, it would be plus 13.5. Let's say you have a mixture, you go in the lab to make 2-butanol, and whatever you do, you end up with pure 2-butanol, but it has an observed rotation of 8 degrees. So what's in the mixture? So what's the first thing that you'd like to know? If you're going to describe a mixture, what would you, like, how would you describe a mixture? What's that? Okay, but what's, like, if you were just going to say, like, when you walk around and you know, trying to think how to You're walking by a classroom, friend, and you're going to say, look in there, that room is 37.5% men. Or what, yeah, which one is major? You wouldn't say it's 37% men. You'd say, there's more women in there. More men, more people in blue shirts, more whatever. We often describe a mixture as like, what is the predominant bit? We actually don't use a lot of quantitative specificity in everyday life. So yeah, I am definitely this problem definitely will end up with you guys giving me a number, okay? But the first thing is just like, what is the major component? So what is the major component? What? Why are you saying S? Right, okay, so the direction of the observed rotation is going to be the same as the direction of the major component. Right? If a mixture is mostly S, then the little bit of R, sorry, I shouldn't even say, right, there are enantiomers that aren't R and S. It would be RRR and SSS, or RSR and SRS. Like, you can have multiple chiral centers. If the predominant enantiomer is plus, right, then all of the minus enantiomer gets canceled out by some of the plus enantiomer, leaving a little bit of plus enantiomer to rotate the light clockwise. So when you look at an observed rotation, the first thing to notice is the sign. That sign will tell you which enantiomer is the major. And then you can kind of forget the sign, okay? So this is, knowing this, we know that the mixture is going to be mostly S. All right, so then you work through this. So the percent EE here is going to be 8 over 13. And you can multiply that by 100. For percent, you probably should. This turns out to be like 0.59. 591 something. That's not, we don't want to do that. And it's 13 and a half anyway, sorry. We're going to call that 0.6. All right, so this means this is a 60% EE. So that means 60% of the mixture is S, right? It does not mean that. So you might not, you got to do some math to figure out what it means. Some of you may have been able to do this in your head already. 0.591, it's a little harder to do in your head. 0.6 is easy, once you know what you're doing. Okay, 60% E. The one thing you know it doesn't mean is that 60% of the mixture is one thing. So percent EE is also going to be percent S minus percent R equals 60. Okay? This works out to be in percent S minus 100 minus the percent S equals 60. All right? So remember, we do this assuming that the mixture is entirely this molecule. All right? All we have is 2-butanol. We have some R, we have some S. And that means the percent of the minor is just 100 minus the percent of the major. In this case, the percent R is 100 minus the percent S. Percent S is also 100 minus the percent R, right? So then you can do algebra. 2 times the percent S minus 100 equals 60. 2 times the percent S equals 160. If you add 100 to both sides, and the percent S is 80. So From that, you know that 80% of the mixture is S plus 2-butanol. I'm going to let you write. That's a lot of, I go almost 4 months without showing you an equation, and then all of a sudden I'm doing algebra. All right. You should double check that. Really, anytime you guys do math, I mean, this is not a math course. I don't do a lot of math in this class. But anytime you do math, you should back check it. Okay? So I arrive at this answer. We're talking about percentages of mixture. It has to be a positive number, first of all. You can't have minus 8% something. And then you got to have, right? We've said S is the major. It's got to be over 50. If you come up here and you get percent S is 30, you have made a mistake of some sort. And then we said the percent EE is 60. The percent EE is the percent of the major minus the percent of the minor. So if it's 80% S, it's 20% R. 80% minus 20% is 60% EES. Okay? So this is how you work one of these problems. This is what all the EE means. There's some of that. There's a little bit of that on the final project you've probably run into. The take home, there's a lot of take homes. Like I said, a lot of you guys, if you wind up using drugs, that's about what I was about to say. Any of you who end up using drugs, you'll know from watching TV and movies that drug culture is really obsessed with enantiomeric excess. That's not true. I've maybe lost you. Nobody was laughing at that. So if you wind up working in a field where you administer or think about drugs, a lot of biologically active molecules are chiral. So there'll be a plus enantiomer, minus enantiomer. And a lot of times, like say you have a drug that's got 8 chiral centers in it. Nobody's going to market that as like the RRS, RSRS enantiomer, right? They're going to tell you it's plus or minus. So you'll see that in the name. The other thing is anything you put in your body that's chiral, the enantiomer of that molecule will have different effects. Remember, different enantiomers interact in a chiral environment differently. Okay, so if I eat R2-butanol, something different is going to happen with that molecule than if I eat S2-butanol. Okay, and so there are some examples, and if you take any bioethics, you'll probably come up with this. The big one is the thalidomide disaster. This was the 50s. We were very much into a better living through chemistry, and you know, that is a mocked. I think that was Dow or DuPont had this better living through chemistry advertising slogan for like 25 years. It's mocked now because a lot of environmental problems came out of it. But honestly, like, chemistry has improved life in many wonderful ways. So they came up with this drug. That wasn't Dow or DuPont. Somebody came up with this drug. I forget who it was. Thalidomide. And the idea was it would reduce nausea. And it did. Like, they studied this drug, and it was a miracle. Like, people with, you know, like really debilitating nausea were almost immediately cured. So you've probably read that, like, drug tests are not usually equitable. And in this case, they had studied this drug almost entirely with men, a few women, but no pregnant women. But who are you going to market an anti-nausea drug to? Like, who are the obvious folks to give this drug to? It's pregnant women. And it turns out that one enantiomer of thalidomide, wonderful anti-nausea drug, the other enantiomer is a mutagen, a really powerful one. And so there were, I mean, around the world, I think it was hundreds of thousands, maybe millions of birth defects from women who had taken this drug, and a lot of miscarriages. Right? And it turned out that they had studied the racemic mixture because, again, over here, two enantiomers behave identically in an achiral environment. It's actually really hard to separate enantiomers from each other. Even today, with modern technology, it's expensive, right? You're a drug company, you don't want to spend any money. In the 50s when they did this, like separating those two enantiomers efficiently would have been really hard on an industrial scale. All right, so today we've learned, today if you want to market a chiral drug, like you've got to show both that your drug is very nearly enantiomerically pure and that the other enantiomer is benign. All right, so again, that's hard. So now, today, a lot of pharmaceuticals are not chiral. Like a drug company would very much like to have their drugs be achiral, because now I don't have to worry about it. Okay, there's a lot there to unpack and think about. I hope you get a chance to do that down the road. Like I said, today what we do, you've done column chromatography and TLC, you've learned some stuff about separating molecules. Today what you do, if you want to separate enantiomers, is the solid phase in your column is, instead of just being silica gel is achiral. So instead of using an achiral solid phase, you use a chiral solid phase. And now as the two enantiomers, like the two enantiomers will stick to the solid phase differently, and that lets you separate them. Now we can, given a chiral column, you can sort of handle the two enantiomers like just, an apple and an orange. It would really be nice to just describe mixtures of enantiomers as that's 85% plus and 15% minus. But this percent EE thing is so ingrained in the literature that that's still the way we describe it. It's all, like I said, it doesn't make sense using today's technology, but the technology used to study enantiomers for 150 years, it was the only way to do it. So I'm not going to ask you a lot of super detailed questions. I'm going to trust you can do algebra. I want you to know what a percent EE is and be able to handle this. I want you to understand why a racemic mixture is so described. And maybe I want you to answer some questions using percent EE data in it. And I'll show some examples of that now. Are there any questions before we move on? All right, so coming back to chapter 7. Draw the product of this reaction. Got to give you some other information. Draw the product and tell me what the EE is. You can tell me what the specific rotation is too if you want. Percent EE. If you think you have all your answers, go ahead and give me an R and an S for the chiral centers too. If you've done the one on the left, I'm going to give you guys like another couple of minutes on the one on the left, but you can try the one on the right as well if you're. Okay, so if we come over to the problem on the left, you've got 2-butanol up here above. It's going to work out the same way. OH is front, methyl to the left, priority 2 thing to the right, priority 2 things over here to the right. This is going to be R. Bromine is 1. Proton is sticking out of us is sticking, not sticking out of us. Proton sticking out at us is 4. Carbon, 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 carbon H. So 1, 2, 3. Counterclockwise circle, but the low priority group is coming out at us. This is also R. I've told you this before. Seriously, do not bank on this on an exam. I tell you this conversationally, right? Chemist to chemist. That if I just randomly draw a molecule, it's probably R like 80% of the time. I don't know why, but I've been doing this a long time now and I've noticed it. Okay, so starting material, does the starting material have a leaving group in it? Yeah, what is it? Br. Remember, hydroxide, OH minus is not a leaving group. So nothing's going to happen to the alcohol in this reaction. Bromide's a leaving group. Do we have a good nucleophile or a strong base? What is that? Cn minus is the good nucleophile. All right, potassium is plus. DMF, you guys will remember from lab. You did an Sn2 reaction in DMF. DMF is a polar aprotic solvent. It's good for Sn2 and E2 reactions. So we got a secondary bromide, so you can do Sn2 and E2. They're beta hydrogens. Temperature is going to give us that this is an Sn2 reaction. All right? So the product is going to be cyanide doing a backside attack on the bromide. Nothing happens to the alcohol. The backside attack, right? If the bromide is away, the nucleophile's got to come from the front. Okay? What is the percent EE of your product? If this is a purely Sn2 reaction, every single time these molecules encounter, they do an Sn2 reaction. It is 93%. All right, so I've drawn here the major enantiomer. I've said it's 93%, so it's not pure. Basically, 96.5% of the mixture looks like that. The other 3.5% has the bromide forward. When the bromide is forward, the nucleophile has to come from behind. Every R carbon that gets attacked will get inverted. Every S carbon that gets attacked will be inverted. And the result is we'll wind up in the same place, 93% EE. So what's the specific rotation of the product? It is not. No way for you to know. I like asking those in class. I probably won't do that on an exam. I don't promise not to, but so I want you to think about it. You have no information that would tell you the specific rotation of the product, all right? This is a completely different molecule now, right? Yep.
If the chiral center with the leaving group was the only chiral center that you said it's negative 39.2?
No.
You know,
No, because now it's still not the same molecule, right? You'd be going from, so if this was just a bromide, now all of a sudden you'd have a cyanide.
Okay.
Yeah, yeah. So you know it's 93%. And so what you could do is you could run this reaction under conditions where you would expect to do a purely Sn2 reaction. And honestly, for that, you'd probably put in a high concentration of cyanide. What you don't want is the bromide to leave and get a cation. Okay, so you'd have a high concentration of cyanide, good solvent for it. You'd want to make sure you did that. And so if you know this is 93%, then you know that that's 93% EE. You can measure the observed rotation, and that would give you the specific rotation. But you'd have to measure it. Okay. Quickly, give me a product and a reaction on the left. And a percent EE. Do you have a leaving group? A few shakes of the head, a few others. This TS is a tosylate. I'll draw that up here. That is a tosylate group. Toluene sulfonate. So toluene is a benzene with a methyl. There are industrial reasons that toluene sulfonic acid is really easy to produce from oil, crude oil. It's a turns out to be a strong acid, right? If you put an H on that on the single bonded O there, that winds up being an acid that's almost as strong as sulfuric acid, which makes OTS minus a really weak base. It's a good leaving group. So that is a good leaving group. Do you have a good nucleophile or a strong base? You don't. Water is weak base, weak nucleophile. So that's going to take us down the Sn1E1 pathway. Could you do an Sn2 even if you had a good nucleophile? How come? Right. So the leaving group is on a tertiary carbon. So there's no Sn2. So if we had any kind of decent nucleophile or base, we would get an E2 reaction out of this, right? And an E2 reaction, you would no longer have a chiral center. Percent EE is not 0 then. It's just like it's a not applicable data point. Okay. So what's the mechanism of this reaction? So no, I just mean like E1, Sn2. It's Sn1. So, right, no strong base or nucleophile, E1, Sn1, temperature's low. We're going to make a good cation. This reaction is going to go pretty well. First step is the leaving group leaving. That's a reversible process. And the Sn1 and E1 are reversible. You get this really nice cation. Is that cation chiral? Nope. So then water is going to come in. Water can come in from the front or back now. That cation is achiral. The sp2 carbocation is planar. Attack can come from the front, back, top, bottom, left, right. And again, water attacks in this situation as water, not hydroxide. The next step is a protonated alcohol, and then water takes one of these protons. You can take either one of those protons, and the final product is an alcohol. Now that is chiral. That is a chiral molecule. You got a chiral center there. What is the percent EE? Sorry? What did you say first time? Yeah, and then you changed to 0. That's a real common mistake. So the answer is 0. Right? And the reason you said 50 is you're thinking it's a 50-50 mix. Okay, so this is going to be a 0% EE. 50-50 mix. All right? The enantiomeric excess of a racemic mixture is 0, not 50. Like I said, enantiomeric excess is really a crazy way to define a mixture. And the point is, so I've said this before, if you have a reaction where all the reagents and all the reactants and the solvents and the catalyst and all that is achiral, if your product's chiral, it has to be racemic. The same is true if at any point during the reaction you get an achiral intermediate. Right? Once the leaving group leaves, you get this achiral intermediate. That molecule has no memory that it used to be R or S. Right? So once you lose the chiral center, now you have no stereochemistry in the reaction. So a purely Sn2 gives inversion. Your EE will stay the same. It'll just, the chiral center, if the atom that is attacked is chiral, its chirality will invert. A pure Sn1 will give a racemic mixture. All right, so let's see. I thought I had a clear picture in my head. I'm going to need to look at something. All right, so we're going to take R2-bromobutane, pure R2-bromobutane, 100% E. That's the only molecule we have in there. A lot of those molecules, but that's the only one. We're going to treat this molecule with lithium hydroxide in water at 30 degrees. And we're going to get 2-butanol. And then we're going to measure the rotation of plane polarized light under standard conditions of that 2-butanol. And we're going to find that our observed rotation is plus 9.2 degrees. So using the data down below, figure out what happened in this reaction. How did the product form? Give you like 3 minutes before I walk you through it. All right. Is this reaction an Sn2 reaction? Is it an Sn1 reaction? So, if it was purely an Sn2 reaction, what would the product be? It would be a pure Sn2 would give pure S-butanol, 2-butanol. Right? So the bromide's out, like 100% bromide is out. So the hydroxide, if it does an Sn2 reaction, would come from the back, you'd get S-2-butanol. So what then, if it was a pure Sn2 reaction, would the observed rotation be? Plus 13.5 degrees. Well, it's not that, because your data says it's not. Just a reminder, and I don't know, I don't want to tick anyone off, but right, when I ask you, like, predict what mechanism this is, remember, it's a prediction. And you can predict, based on empirical data, what ought to be the dominant mechanism, right? So if I had asked you this, based on the flow chart, if I hadn't given you the product or any data, right? You got a leaving group, it's on a secondary carbon, there's beta hydrogens, we can do Sn2, we can do E2. You got a strong base, good nucleophile. So we're going to do Sn2 or E2. Temperatures below 40, you'd probably predict Sn2 as the major product, right? If all I had given you was sort of this, and, you know, let's include our EE friend now. And if that's all I'd given you, you would predict S2-butanol 100% EE. Because you'd predict an Sn2 reaction. Okay? But this is not a prediction. This is an explain observed data. Once you have data, and this is going to be true for the rest of your life in any kind of field at all, not just science. Like, once there's data, you can't just, like, make up other stuff. Clearly you can. Make a lot of money doing that. But to be right, you can't do that. So here, the fact that this observed rotation is not plus 13.5 tells you it is not a pure Sn2 reaction. If it was pure Sn1, what would the observed rotation be? It would be 0, right? In a pure Sn1, the leaving group leaves, get a cation, water comes in from one of the two directions. Polar protic solvent, Sn1 with a secondary cation can happen. But again, it's not 0. So what is the answer here? No. Some E2 might have happened, all right? So E2 is definitely something to wonder about. If I said here that your percent yield was 41%, I should have done that. That would have been a good question. I did that on purpose so as not to fall. All right, if I had said the yield was 41%, now E2 is a good explanation. Why is the yield so crappy? Oh, well, look, you got a strong base, secondary halide, temperature's getting a little, you didn't cool your reaction. Looks like you did a lot of E2. Be an excellent explanation. But I've said, if I don't say that, okay, so, yeah, I didn't say that. I haven't told you anything else is there. Let's say the yield is 94%. Yield's fine. So how do you get an EE between an Sn2 and an Sn1? Do what? You could do both. Now, one molecule can't do both. All right? So this one molecule can't do both Sn2 and Sn1. But again, you don't have one molecule. You've got, 2.4 times 10 to the 22nd molecules. Some of the molecules do an Sn2 reaction, and every one of the molecules that does an Sn2 inverts. Based on the fact that the observed rotation is a fair percentage, like this is going to end up being like 70, 75% EE. Most of the molecules do an Sn2. But you have a lot of molecules that don't, right? That do Sn1. So the fact that, the temperature's a little higher, the solvent supports formation of a carbocation. Every molecule that undergoes Sn1 has a 50-50 shot at turning out to be R or S. Right? I can't emphasize this enough. A lot of people tend to come away thinking Sn1, you keep the stereochemistry. You don't keep the stereochemistry, it just becomes racemic. So every molecule that does Sn2 turns into an S enantiomer. For every 2 molecules that do Sn1, you get 1 R and 1 S. All right, so when you see a loss of stereochemistry, that loss of stereochemistry, if it doesn't go to 0, like if it goes to 0 or really low, right? Let's say your observed rotation is like 3% EE. That's mostly an Sn1 reaction. But if it's high, so you still have mostly 1 enantiomer, but not purely from a pure enantiomer, that's going to suggest that you have a mixture of mechanisms. All right, so, and that's going to be true. And the idea that E2 can happen, most of these reactions in this chapter, if I have conditions that can do Sn2, they can probably do E2, they can probably do E1, they can probably do Sn1. And honestly, usually a non-zero amount of all of those are going to happen. You're not going to have to worry about that so much, except in the famous word problem like this. And you'll see some of that in old exams where it's like, here's a whole bunch of products. Basically, you're having all these mechanisms happen at once. When I ask you to predict the product, I'm asking you to use the flow chart to predict what you think is most likely to happen. I've gone a minute over. I apologize. I'll see some of you this afternoon. Good luck to that group. Everybody else, I've been asked several times if I will have office hours this week. Yes, I'm having office hours this week. They'll be tomorrow and Thursday, probably Friday morning. I'll have them posted this afternoon. I apologize I haven't had them earlier this week, but I have not been available Monday or Tuesday. Are exams 3 not? There are no exam 3s on? Yeah. So, well, I'll talk about this later. I'm over. Student evaluations, you should have gotten an email about evaluations for your classes. Please put in there, I'm not going to be mad at all, like if you tell me I suck at Canvas. That is, I share that evaluation. And I'm sorry about it. So yeah, I'll get exam 3s up. I'm going to, while people are taking exams this afternoon, I'm going to do some Canvas stuff.
Okay, I have a quick question.
Uh-huh.
So on E2 reactions, where the leaving group is not anti-coplanar to H on the beta hydrogen, you can change the molecule conformation to make it.
Yeah, but that usually changes the stereochemistry of the alkene that comes out.
Oh, thanks. I'll see you later.
Okay, so you can rotate it.
The molecule will rotate, so it has to be. If it can't rotate to make the H anticoplanar, it won't do an E2.
Okay.
But that rotation might change. That's going to affect you get an E. Yeah.
It's like, I guess it's this one right here.
Yeah.
BR and the methyl can rotate.
So figuring out whether those 2 methyls will be cis or trans, you have to do like a Newman projection to figure that out. Yeah.
So since